everyone. Thank you for attending Sensors Innovation Week Summer Edition, presented by Fierce Electronics and Sensors Converge. My name is Charlene Susi, Senior Director of Sensors and Electronics, and I'm delighted to be your host for today. Before we get started, I'd like to thank today's sponsors, Nuvation and Rohde & Schwarz. This afternoon's session is focused on embedded systems with a theme of IoT devices, strategies, and tech innovations that beat the heat. And so you can best prepare yourself, here's a quick rundown of the sessions. First up, Whitmarsh Research Group's co-founder, inventor, and industrial designer, Shanna Whitmarsh, will be delivering the opening keynote. At 2:15 p.m., Rohde & Schwarz's Mike Schnecker will be giving a partner keynote. At 2:30 p.m., Tim Hiller, Nuvation's Director of Engineering, will deliver a tech talk. And closing us out at 2:45 p.m., we'll have our main panel led by JLL's Chief Information Officer of Digital, Edward Wagoner, with speakers from BlackBerry QNX, 42 Technology, NXP, and Rohde & Schwarz. As a reminder, we love questions, so be sure to submit your questions and answers in the Q&A tab on the left side of your screen. Our partners have provided all sorts of resources too, so be sure to check out the Content Hub tab. Lastly, we've added a new virtual networking feature called Meet the Speakers, which will take place at 3:30 following the panel. All attendees of the panel session will be automatically redirected to the networking event. Or to join separately, select the Meet the Speakers embedded track block on the sessions page. Look forward to seeing everyone there later today. Okay, now let's begin. Shanna, please go ahead.
Hi, I'm Shanna Whitmarsh. I'll be discussing how AI blockchain sensors can manage and direct objects in smart cities by using decentralized blockchain structures to authenticate, process, and create safe, efficient pathways to object destinations. When I refer to objects, I'm referring to current and possible future traffic in a smart city, such as autonomous, non-autonomous, and legacy cars and aircraft that travel by air, land, and sea. Today, I want you to imagine smart cities using a sensor that has an AI and blockchain chip that communicates with an AI blockchain local server and an AI cloud server in a closed system, controlling entire traffic systems in the air and on the ground, eliminating traffic jams and accidents. In this presentation, I'll take you along our research path, our results, the integration of artificial intelligence and a blockchain platform to communicate with an AI blockchain sensor that can command and control all types of traffic within a smart city. In 2014, we began experimenting with artificial intelligence managing aerial and ground traffic using AI sensors. We also wanted to enter the fintech space with a decentralized finance product by experimenting with different blockchain platforms to develop a sustainable crypto commerce platform. As we were working on both research projects, Peter Whitmarsh, WRG's co-founder, and I decided to make the programming and scripting process faster and more efficient. We developed smart code that was separating the functionality of a program into independent, interchangeable modules that could each execute only one aspect of the desired functionality. I guess finding shortcuts is the sister to all inventions. We were surprised to find that these smart codes were interchangeable and could work for both AI system and the blockchain platform. We developed a strong security interface with several algorithms with interfaces that were built and integrated on the secure hash algorithm process called the SHA 256-bit hash, using a 4-bit string process. As you can see in this slideshow how an extracted hexadecimal address would look, with a quick explanation of what the SHA 256-bit that can be reviewed later online. By creating an AI blockchain engine, we were able to create a robust, artificially intelligent blockchain system that resides on our AI servers. The machine learning process creates random addresses for every object that enters the smart zones, which can have up to a 50-mile range. The AI blockchain sensors can receive the instructions from the machine learning program to apply a temporary address on every object entering the smart city. We call these temporary random addresses the AI Smart Pass address. And that's transmitted from the AI chip in the AI blockchain sensor to the AI blockchain chip that's on board every object requesting entry into a smart city. The AI Smart Pass address is a unique hexadecimal code that binds to every object ID's hexadecimal marker. The AI blockchain sensor's AI Smart Pass address binds to an onboard unique broadcasting ID hexadecimal address signature value. This is the ID marker. It can help objects to access expressways, to control it for autonomous driving or flying, or guide it by delivering instructions to commands to the onboard AI signature chip. What's interesting is that the object's ID marker signature value is like the registration IDs that you find in car registration stickers, which are unique to the VIN number of each car. In an AI traffic management environment in a smart city, the AI blockchain sensors are constantly in communication with the bonded object's ID markers as they drive or fly in smart city zones. These ID markers help the AI blockchain sensors to facilitate the creation of routing destination waypoints into the ID marker chip, which establishes a control for safe travel and the ability to act in case of an emergency where a command and control is activated by the AI blockchain sensors. By monitoring the object's movement and continuously transmitting instructions and commands to an onboard AI smart microchip, it prevents collisions and congestion. The AI blockchain sensors are binding moving objects. This process is a handshake between AI blockchain sensor control connections on an object's destination path while simultaneously feeding information and data to the AI local servers and AI cloud servers. This communication is decentralized to where all objects in the smart city are in communications with all AI blockchain sensors, all AI local servers, and all AI cloud servers that are within the closed network of that smart city, and any other smart cities that are broadcasting their access connection address. The AI local servers are the control exchange between the AI cloud servers and the AI blockchain sensors. The AI engines on the local servers manage the information and data ingestion and transmit to the AI cloud servers. The information and data that's collected and archived by the AI cloud servers are passed into the machine language, deep learning, big data, and the predictive analytics programs where the system learns from the data to understand traffic events, to analyze them and create solutions. The machine learning module learns and evaluates macro traffic events that'll disrupt the flow of air and ground traffic. Its macro data is communicated to the deep learning module and the predictive analytics module. Instructions are then created at the micro level for solutions, commands, and controls to be acted on by the AI blockchain sensor. One critical example is when the AI blockchain sensors are unable to authenticate an object that they detect attempting to enter a smart city airspace. The AI blockchain sensor sends 3 commands. The first command would be a safety and avoidance sequence, getting other objects into a safe alternative pathway. At the same time, a communication is sent to the unidentified object on all broadcasting bands when it's 45 to 50 miles from entering the AI smart city zones. The AI program communicates 3 options through the sensors. 1, pay for an AI smart pass address token to access the smart city. 2, turn around. 3, land outside the smart city zone. If the unidentified object continues to the city without taking one of these 3 actions, the AI program activates a defensive command and control program to commandeer the object. Even if it's a legacy drone, for example, or an autonomous car, the AI smart defense program would move it to a safe zone within the smart city or outside it. If it's a legacy car that doesn't have an AI smart pass address, the information about the object without the address handshakes directly with local law enforcement to stop the vehicle. This is no different than being pulled over for driving with an expired tag or expired plates. This is just a small example of what the AI blockchain sensor can be programmed to do. We're still in the experimental stages, expanding the command and control programs. Here we're illustrating the use of smart programming to advance data collection with the AI machine learning that's interacting with the deep learning part of the AI blockchain system. Algorithms are created to record different incidents and create a command and control database to retain these types of actions in memory, building on them for better solutions to random complex occurrences. I'll explain a little more in detail how the AI blockchain sensors interact in real time with the AI local servers and AI cloud servers simultaneously. The key is the AI microchip that every sensor has in their system. It's constantly running predictive analytics scenarios, returning the results data in milliseconds to the AI local and AI cloud servers as they interact with the AI's deep learning module to teach it the different types of solutions for events. It uses this information to create proactive safety protocols and parameters for objects to fly or drive in their pathways. From our AI research, we surmised that all objects would eventually have universal onboard agnostic sensors with AI signature microchips. These could be installed at the factory level or become available for aftermarket installation. Just like windshield wipers, we see the agnostic sensors and the AI signature microchips becoming a plug-and-drive or plug-and-fly solution that have become a mandatory part of state licensing processes to certify vehicles to operate safely within a smart city. There are many possibilities for AI blockchain sensors to command and control moving objects with the communications facilitated by AI access microchips, each with a unique hexadecimal string ID marker. The AI smart sensors with AI access microchips on objects flying or driving with a smart city would make it possible for the implementation of an AI traffic management system. However, during our research, we found that we needed a faster way to process the information and to avoid latency as the traffic increases and nodes on the network get congested and become slower. The AI big databases could handle the back end of the system function of ingesting data, exploring, analyzing, visualizing, and creating solutions in real time as it processes complex big data in milliseconds. However, we needed to find a way to increase the speed sufficiently to relay data to the AI local server database or the AI cloud server database and back to the AI sensors. We weren't satisfied with the processing speed in real time of the AI smart pass address hexadecimal strings. We theorized that all AI smart pass address hexadecimal strings that bonded with all AI signature ID markers both had hash headers in their bounded hexadecimal addresses. If we were able to split the hash headers and store them on the AI local server and the AI blockchain sensors and send the hexadecimal strings, the AI smart pass addresses, and the ID marker addresses, and store them in the AI cloud server, we might be able to increase the real time of processing actions on the fly. We found that AI blockchain sensors could disseminate the command and control instructions fast enough, but the two-way relay communications to the local servers had latency issues. We were running an 8 GPU rig that we replicated from the crypto commerce system we were building, which didn't use as much energy. But it was frustrating to have to keep up the AI local server from overheating, which it did, and it would shut down. Adding to our frustration was the mass energy usage and massive electric bill. We needed a more sustainable solution to create hexadecimal addresses reliably. We found that the Python codes we were writing to generate the encrypted codes from our crypto commerce experiment that was running on a Quorum Oxen hybrid platform could be applied to a smart city environment to sell access for one-time use or subscriptions. The advance of that platform is the private, secure, closed network nodes allowed better authentication processing. By using the blockchain protocols within a private blockchain network node, the Quorum Oxen hybrid platform gave us a higher security format with a robust authentication processing for higher volume of processing and bonding the AI smart pass addresses and the objects IDs markers at hundreds of thousands of transaction bindings per second. We discovered by accident that our AI sensor smart code would send the body of the hexadecimal ID strings to the AI cloud servers, while the hash headers of the hexadecimal strings were stored on the AI local servers and the AI sensors. This allowed us to increase the execution volume of commands for authentication by looking at just the hash headers of the bounded hexadecimal addresses. The reason is that in the authentication process, the AI cloud servers would store the AI smart process address hexadecimal strings and the object's ID markers addresses hexadecimal strings. In theory, this type of process would increase the transaction bindings per second from 10,000 to some X 100,000 transaction bindings per second. By integrating a smart code splitter with the new AI server systems that use less energy, it allowed us to utilize non-carbon energy resources. We were excited to see the multi-communication speed increase. We applied these Express AI Python smart codes to the AI blockchain sensors firmware. The new platform responded without error to the data information being sent by the AI blockchain sensor. The new Express process code was faster in sending the bonded hash headers to multiple AI local servers and AI sensors at hundreds of thousands of transaction bindings per second. And at the same time, the Express splitter was able to prevent the latency that had been occurring. We named this discovery the Blockchain Express Splitter process. Here's a characterization of how binding a transaction would occur. We used the example of money to illustrate the concept more easily. This slide illustrates the principles of how the binding occurs. It's one of the foundations of the Blockchain Express splitter. So the research has led us down a path to where we envision that the AI blockchain sensors will enable smart cities to have powerful command and control of their transportation zones. Using the blockchain splitter code as I've described would increase the AI blockchain sensors' communication speeds of command and control executions in the hundreds of thousands of binding transactions per second. This expanded functionality could accommodate higher volumes of AI smart pass addresses, hexadecimal strings that can bind to vehicles. AI blockchain sensors would be instrumental in processing command and control instructions to manage the traffic in smart cities of different types of objects that are moving in all different directions and altitudes simultaneously without collisions. Today, I've presented a small sample of how two unique systems, which when combined and integrated to create sensors within an AI blockchain platform, will encourage new and exciting enhancements for sensor hardware and firmware, and in many applications, create more robust and sustainable performance. Get ready for the future of smart city traffic management with AI blockchain sensors. Thanks for joining me today to visualize this interesting path for the future of AI blockchain sensors within a smart city.
Thank you, Shauna. Up next is a partner keynote from Mike Schnecker. Please go ahead, Mike.
Thank you very much for including us in this session. Roden Schwartz is a fairly large company, been around for a long time, about more than 85 years, family owned, and we specialize in the measurement, test and measurement industry. And most of what we do is things like wireless testing, as well as even cellular networks and EMI testing. But for today, I wanted to focus on a little more basic type of measurement, that being the use of power in sensors. So a lot of sensors are remote, and so they are often battery powered, but heavily integrated. So you typically would have a microprocessor, you might have some memory. In addition to that, you have sensors typically. You might have some wireless connectivity. In a lot of cases, you do have wireless connectivity. And all of this things needs to operate efficiently. And we worry about things like, for example, battery life, but also just power consumption as the number of sensors grows in a network. And if you think about some of these battery operated things, they might have to operate for days, weeks, even months unattended. So power consumption becomes very important. As an example of power consumption, here's an example of a Bluetooth low energy device. And what we're showing here is a plot on the left-hand side is actually the electrical current being drawn from the power source. In this case, it would probably be a battery. And there's different parts of the operation of the device during which the power or current consumption changes. For example, there's a sleep mode on the far left edge of the red curve, which indicates the power drawn when the device is just idle, sitting there doing nothing. And then maybe it's addressed and then it's going to power up. And it might be doing some RF transmission here where the current gets very high. And then it might drop down into a non-transmitting state, but still the CPU is operating. And so we have a current draws over there as well. So what this allows us to see is the power usage of a device that's often software controlled. So this is kind of the software hardware interface. Can we understand how much current is being drawn at any given moment in time so that we can optimize this for battery usage, making sure that we're not, for example, turning on systems that aren't necessary, drawing extra energy. And this often becomes complicated by the fact that what you think the software is doing, the hardware is not exactly doing. And there's hardware imperfections that could be causing extra current draws as well. One of the challenges, the main challenge of this, is that you're talking about devices that draw very small currents. So the challenge is for measurement is to measure very, very small currents. And there's essentially two different ways to measure small currents. The first way is to use something called a clamp-on current meter. This is a device that clamps around a power lead, and it provides an output voltage that's proportional to the current flowing through that loop. The other method is something called a shunt resistor, where you essentially put a resistor in series with the power source and you measure the voltage drop across that resistor. The clamp-on devices are typically not very good for low current measurements because of the sensitivities aren't really that good. So for things like microamps, where you are with a lot of these sensors that are remote using batteries, it's actually probably not sensitive enough to do the kind of measurements necessary. So it leaves us with the shunt resistor method, which is most commonly used for the small currents. Now, typically you want a fairly low resistance value, maybe on the order of 1 ohm, maybe less than an ohm typically, because you don't want to drop a lot of voltage across that resistor, which might cause your device to stop operating. You want to have a minimal impact on the operation of your device. The result is, and the challenge is, that on the instrument where you're measuring it, and typically this is an oscilloscope, you'll be looking at microvolt levels on the instrument. And the sensitivity of the oscilloscopes typically are in the millivolt range, typically you have 1 millivolt per division as sort of a minimum on most oscilloscopes. So you have this challenge that you've got a very small measurement amplitude and a very limited amplitude range on the instrument that you're trying to test. Another problem with the shunt resistor method is you have to use something called a differential probe. This is a probe that does not have a ground. And the reason for that is there is actually no ground reference across that resistor. So you would typically have to use some sort of a probe that doesn't reference to ground. These are available, but typically they're what we call 10x probes. That is, they attenuate or they reduce the amplitude of what's being seen across the resistor by a factor of 10. And so that tends to just exacerbate the sensitivity problem that you already have. And so that the two main issues then, of course, are the sensitivity and the probing. Then you also, I guess, with the clamp-on probe, you do have drifting issues, although the clamp-on probes, again, probably are less applicable here. So why are they difficult to measure? As I mentioned, they're difficult to measure because they're very small. And here's an example of what I'm talking about graphically. So on the right-hand side, we've got two plots essentially of the same thing. It's a device switching from a low current to a higher current, in this case going from nominally 21 milliamp draw current to 53 milliamps. In both cases, this is probably more current than a low power device would draw, but it's an example of how the measurement accuracy works. If you look at the upper display, that is measured with a standard differential probe, what we call a 10x probe, across a shunt resistor. In this case, it's a 0.1 ohm shunt resistor, which is a fairly common value for doing these measurements. And you can see that the sort of noisiness across the waveform is actually showing the sensitivity of the measurement. You can see there's a lot of variation in the range of a few hundred microvolts on that signal. So your accuracy, if you try to measure a change in the microvolt range, you wouldn't be able to see it simply because of the uncertainty caused by the additional noise of the 10x the 10x oscilloscope voltage probe and the load resistor. The lower display shows an alternate method using a specialized voltage probe. This probe is designed specifically for this application, and it has two things that enable it to be very effective here. Number one is the inputs are differential, so there's no ground reference, and so we don't need that. And they're actually not 10x, but rather 1-to-1, so you don't have that signal loss being caused by the probe, which results in the additional noise. So this gets rid of sort of the noise problem. The second issue is the dynamic range issue that you have with oscilloscopes. And to address this, the probe uses an 18-bit analog digital converter. Most oscilloscopes these days are using 8 bits. There are some 10 and 12-bit oscilloscopes out there, but even those effectively don't have very many bits owing to the bandwidth of the scope, so they're really not specialized for this application. So the specialized probe allows you not only to get the lower noise, but also to get the dynamic range that you need to see the very small currents. And so on the right-hand side, I'm showing a measurement with the same setup, but the same actual setup, same change in current. But you can see that the accuracy, the noise on the trace is much smaller, allowing us to see much smaller variations in the current draw. So this next one here, we're showing just a very quick block diagram of what we're talking about. So you can see the unit actually has multiple current voltage inputs. So you could actually do up to 4 on one of these modules. So you could have 4 voltages and 4 currents. This is helpful because a lot of devices have multiple power rails. You can actually measure individual ones separately. Behind the inputs, there are the 18-bit ADCs that digitize the voltages that we're measuring and the current as well, so you can see both voltage and current. And then there's an independent memory for each channel. So all the measurement apparatus is contained within this box, which you can then plug externally into an oscilloscope. And that way you could actually monitor the voltage rails. And at the same time, on the oscilloscope channels, you could, for example, monitor sensors or RF signals at the same time. So you can see correlation between voltage, current, and external signals that may be sensed by the device or also might be transmitted by the device. Just to give you a quick idea of the ranges that one can see, this is an indication of what's possible. So you can measure, for example, about 381 microamps on the low gain range and about 38 microamps in the high gain range. So you're able to see extremely small currents very accurately with this probe. And so this is sort of the benefit. We're able to see the small current and measure it accurately, so you can accurately predict, for example, battery life or any of the power usage of these devices. So moving on, as an example of how this looks on a measurement. So we're actually showing, oops, I clicked too many times, sorry. There we go, back up. So this is an example of a measurement. It might be a little hard to see. Hopefully it's not too bad. The upper display is showing the supply voltage versus time. And the next grid down is showing the current versus time. And you can see one of the interesting or expected results is that as the current is higher, the voltage would be lower, which indicates when you're drawing a lot of current out of a battery, you could have a voltage drop occurring, which is not uncommon. And the third one down from the top, the third grid down, shows the a zoom. It's actually a close-up of the current. And what we're trying to show here is the very small sleep current that just a particular device has. It's extremely low in the tens of microamps, and we're actually able to measure it. So again, having this kind of a tool allows us to see how much the device is drawing, not when it's on and transmitting and operating, but even when it's off. And so it gives us an opportunity of where we can optimize either the design or even the code that's driving it to minimize power consumption. You can also do things, for example, like math traces. So I can actually take the voltage and current that I measured, do some math, and then provide the power or energy consumption. So again, you can directly take that waveform, integrate it, and indicate how long the, for example, battery might last, given this type of operating scenario. So the nice thing about having a tool like this to measure what's actually going on in the hardware is you design software to minimize power consumption. This allows you to verify that what you thought your software was doing, it is actually doing. And in the real world, you always have to make sure that the hardware is following along with what the expectations are. So that was a very quick overview of just some of the techniques that we can use for low power measurements to help understand, for example, battery life and reliability in these sensors. And just one example of how we can use instrumentation to make these things happen.
Thank you, Mike. Next, we'll hear from Tim Hiller, Director of Engineering at Nuvation. Tim, please go ahead.
Thank you, Charlene. Okay, let's step in here. As you mentioned, I'm Tim Hiller, Director of Engineering from Nuvation's Engineering Design Services Group. This department handles outside customer projects and solutions. Today, I'm going to just give a very short intro to Nuvation for those not familiar with us. And I'm going to walk through two case studies of projects that we've worked on that illustrate low power processing and the need for architecturally creative solutions to fit more into a smaller footprint. I'll make a couple comments on some new technology that came across my desk and some concluding remarks. Nuvation's been in business since 1997. We've done over 1,000 projects, ranging from startups to Fortune 50 companies. We specialize in hardware, embedded software, FPGA design, and manufacturing engineering, transition to manufacturing, and testing. We bring multidisciplinary support to people from medical, industrial. Basically, we've done every project out there. So we have markets across the whole spectrum. And if someone doesn't know it here, someone else does. One-stop shop. We do hardware design, embedded software, system architecture, FPGA development. The markets, medical and life sciences is very popular right now, obviously given COVID. Data acquisition control, industrial automation is always in the background and popular. We have our own energy Nuvation Energy group for battery storage. And we do turnkey product solutions, transition to manufacturing, Internet of Things. This is about 10% of our client base that we've serviced over this time. We have others not listed here, such as Microsoft, Google, and Facebook. For the first case study I've chosen, and this one goes back to around 2013, and this is a project that I worked on the architecture and managed for our customer. And it's a very typical Nuvation project. A customer with expertise in a particular area, in this case, it was acoustic analysis of water leaks in piping, came to Nuvation needing a hardware platform that could be deployed in the field for 5 to 10 years, run continuously without any maintenance, listening to pipes to detect pipe bursts, and also locate ambient leaks in the underground piping. Fun fact that we learned during the project, cities lose about 30 to 50% of their potable water every year to infrastructure leaks. So there's an immediate return on investment and business case for this type of technology. So to develop this, it had to be low monitoring power, but their algorithms required an advanced fast Fourier transform to be done in order to do the analysis. So the solution in reconciling these two was doing a split processor solution, which I will go into in a minute, and how one task hands off to the other. And I chose this project not because it's the newest technology, but because the trade-offs that you have to make and the approaches you can take are relevant today with the lower power sensors that are being introduced by other speakers. And we affectionately called this the muffin board during development. So the DSP processor we chose was from TI, and it was ideally suited to this. It had hardware blocks for fast Fourier transform processing, which were lower power even than DSP could execute. We were talking nanojoules per butterfly. It had significant memory to do the analysis. However, it had very high static current consumption. Just merely having it on in sleep mode would have sunk the entire power budget for taking years off the life of the runtime of the battery. So basically, we had to leave this thing turned off all the time. We added an application processor on the front end of it, which was low power. And it is a traditional approach like Mike was talking about, where you sleep most of the time, waking up when you need to do your processing. And that's very standard in this industry. What we had to do, though, is we had to actually detect a pipe burst. And that's a lengthy event, relatively speaking. And it's always preceded by a significant high impulse adjustment as the first event happens. So what we did was we used two ADCs. One is needed for detail analysis later on to make sure it is a pipe burst. The lesser ADC, that's only 10-bit, is much lower power. And we could set the thing up to acquire samples into a circular buffer continuously using DMA and leave our processor asleep all the time. And this actual ADC had a built-in window comparator, which was ideal because it could detect when we go over a certain level. It'll wake the MCU. We retain the buffer, fire up the more sensitive ADC, continue capturing enough data to then hand it over to a DSP to evaluate, saying that really was a pipe burst event and not someone banging on the fire hydrant. So I do on the right-hand side here, this is the setup that was used. If you are using a device that lacks an internal comparator, you can always add an external one and run it into a GPIO line to give you that capability to do that. So this made a dynamic change in power. The lesson here is it's not just I'm asleep and now I'm awake. It's just, I'm asleep, I've woken up a little bit, and then I'm going to assess whether it makes sense to wake up further and spend even more power. So as long as you can avoid false negatives and risk a false positive event and then go back to sleep if it was false positive, then you can end up saving power in the long run. The other interesting case here is, I'll call it the race to sleep condition. Quite often when people are designing systems, they'll say, okay, we're going to stay asleep, use as little power as possible. We'll wake up. Now we're going to run as fast as we can to finish what we're doing so we can get back to that low power sleep state. The problem with that is it isn't always the winning strategy if you're measuring energy. And I've drawn a little equation here for you. The amount of energy you're spending is dependent on power times time. And if you were to run slower, drop your voltage, you'll save more in the long run because it's a squared relationship. Not strictly correct because it's less than, There is still that static current consumption, but the dominating factor will be how fast you're running and for how long. So the voltage is what ended up costing. And in the life of the product, this translated to better part of a year extra runtime. And the only difference between running at this speed versus this speed was about 500 milliseconds of analysis and delay, which this application could accept. Okay, so summarizing lessons, lower energy tests can avoid higher energy based on probability. Take your work and say, I'm asleep, now I'm awake, and then split your awake time into different levels of tests that you can transition between. Every wake up costs, and that energy frequency relationship is discussed in this paper that I've cited. One thing we found was the oscillator type that we used on the microcontrollers actually had a long-term effect on this. A lot of the microcontrollers will have either an RC oscillator or use a crystal, or MEMS nowadays. The amount of power you require to start up is dependent on the type. And you can sometimes have two oscillators start up to the level that you need. Excuse me for a second. Drying out here. The time you take to start up depends on the oscillator you're using. You don't need a high accuracy oscillator if you're just computing. You need it if you're communicating using a radio or a UART of some kind. Otherwise, stay at the lower power alternative. One of the lessons learned was those analog front-end components, the signal chain that takes the measurements and feeds them in, people will spec components and they'll say, well, I want very high gain bandwidth product or some feature of it. You pay for that because it'll have a higher slew rate and require more power. So actually finding the maximum you need and then selecting the minimum component that satisfies that will save you. And that was actually something that we had handed to us and we had to correct. Standard advice for any embedded designer is if you have partitioned power domains in your system and you're shutting systems down and turning them off, make sure you park any signals going to them so you're not back powering and leaking power into them. And if you have situations where there's lines that require pull-ups, you will need bus switches to disconnect them. Otherwise, you're just going to end up fighting yourself. Also, when switching off subsystems, you want the bulk capacitance to actually be on the high side of the switch, and you want a very low on-resistance switch. The reason, okay, thank you, Grace, for that is you'll spend more energy charging that capacitor every time you wake up. And if you're coming awake and asleep, you're going to throw away a lot of power. Okay, I'm going to have to step ahead here a little quicker. Autonomous sensors can keep you asleep longer. We used an accelerometer to detect tamper events, someone opening the valve. It was doing the checking on its own. Some battery chemistries will basically, we drew so little current, the battery actually passivated. We had to put some extra circuitry in to prevent that, and it actually, the battery thought it was on the shelf. We were drawing so little. I'll move through very quickly through this one. This is a second case study. This one I called out more as a comparison of how it was done then versus how the newer sensors and technologies today would make it an improvement. So I don't need to go in quite as much technical detail for the lessons. This was a personal security product designed to be worn, connected to a phone. It was doing an always-on voice listen for a panic word. It would save the audio, do a two-way phone call to a security call center to deter an assailant, start capturing video or images to send as evidence. So, and it was a very small form factor. And it had a very asymmetric power domain. It had a small battery, but it had to run standby for 12 hours, listening all the time. And then when it woke up, it had to be able to run for 120 seconds active at a very high power draw. So that looked like a standby mode, which was 15 milliwatts. We had 94% efficiency there. And then we had an active mode, which was 800 milliwatts for those 2 minutes. So it led to some design challenges. I put a little picture here. This was the accelerometer we were using for tap detection. And it has this engine built in, which will do the state machine to detect events. while we're asleep. Again, similar strategy. This project uses DSP audio class for doing the wake word detection. It had to maintain phone connectivity and do the gesture. And when it woke up, it basically saved the recording, made the two-way phone call, bright white deterrent LED to attract attention. It had an image sensor, and it actually had an onboard JPEG hardware block. So we weren't compressing anything. The image sensor was giving us the snapshots directly, and that was more power efficient. So look for products that actually have a higher level of integration. It would store everything to a low power flash first, and then offload that to the phone. And if we were to redo this today with newer technology, this was about 5 years ago, we would have switched to Bluetooth Low Energy because they now have the audio profile, which they didn't at the time, for two-way voice. This would also avoid the need for Apple's MFI authentication hardware because we were forced into using Bluetooth Classic, and they police that. So that's further power savings. We would have switched to one of the new MCUs that have a neural net core. And that would have taken us from 10 milliwatt to listen for the wake word all the way down to 1. And I have one slide on that I'll present in a second. And this trade-off means we could reduce our standby power by 60%. That means that a product that was good at lasting for 12 hours could now last for 33 hours and still wake up for 2 minutes. Or we could last the 12 hours and wake up for 12 minutes. You could use these power savings, but you could not actually decrease the battery size, which was interesting. The power was so asymmetric that the max C rating of it would be exceeded if you tried to make a smaller battery. So we couldn't actually reduce the size anymore. A few sensor technologies I'll just mention in passing before I conclude here. What's in vogue now is a lot of neural network processing. ARM has their IP cores, the M55 and Ethos ecosystem, which is being rolled out to products. Syntiant has their NDP 120 processor. It could have done the always-on voice detection in 500 microwatts instead. For vision-based higher power processing, Umbrella now has AI vision processors out, which can do people tracking and threat assessment. In evaluating these projects, we went through Ambiq Micro's portfolio. They have a 14 nanoamp real-time clock chip that can wake other components, so you can really sleep if you want. Apollo has a class of MCUs, and they now have added Bluetooth. They're M4F Cortexes, but they're sub-threshold, so lower voltage. So they'll run at about half the power level. Some newer sensors I found interesting crossing my desk. Thermal imagers over I2C, relatively low resolution, but very low power for certain types of sensing. A new 3x3 millimeter echolocation sensor which is about good for 5 meters. And there's also now a very low power radar chip, which can sense people locations within 3D space. Concluding remarks, we'll say that the embedded design power management practices remain fundamental, what I talked about in the first test case. Newer sensor technologies are providing more capable at lower power levels, but that you can still make them better using these techniques. Look for sub-threshold, smaller node geometry processors. Processors have integrated coprocessor blocks, crypto DSP neural networks. Lower power memory technologies, FRAM, MRAM, and PSRAM are now being integrated onto processors instead of traditional SRAM. Nuvation looks forward to working with you on your next design and working through your challenges. Thank you very much.
Thank you, Tim. Coming up, we will be welcoming our main panel led by Edward Wagner from JLL with speakers from BlackBerry QNX, 42 Technology, NXP, and Rohde & Schwarz.
Hi, everybody. I'm Edward Wagner. I'm the CIO for digital at JLL. You may be wondering, why is the CIO of one of the world's largest real estate companies moderating this panel? Take a moment, look out the window, no matter where you are. Every building you see, every office, industrial, manufacturing, healthcare, hotel, retail building, every one of them, we believe we can drive better utilization, we can better maintain and manage, we can give you a better experience through the use of sensors. So I have a lot of interest, and the panel today has a lot of expertise, and I'm excited to have them join us to walk us through. We have different perspectives, and so I'm going to ask each one of them to introduce themselves based on the perspective that they'll bring. And we'll start with hardware perspective and Rob. So Rob, if you could introduce yourself to the audience.
Hello, everybody. I'm Rob Oceana. I actually, NXP Semiconductors here in Austin, I actually manage the software development department enabling all of our microprocessors and microcontrollers. So looking forward to the discussion.
Thanks, Rob. Next, talk about software. Stephen, if you can introduce yourself to the audience.
Yeah, my name is Steve Olson. I'm a principal field application engineer with BlackBerry QNX. I've been in the real-time operating system space for over 25 years and have focused in on areas that needed safety and security. Those have really been the mainstay of my career.
Great. Thanks for joining us, Steve. Mike, you represent diagnostics and analytics, so introduce yourself to the audience, please.
Hi, I'm Mike Schnecker. I'm with Rohde and Schwartz, and we're mostly in the test and measurement business in the U.S. here, and of course worldwide. I'm actually in the U.S. Up in the Northeast, so we're covering a lot of geography. And I've got 30 years in test and measurement, mostly in things like oscilloscopes and voltage measurement, but also some RF experience.
So you three guys bring a lot of capabilities. I've got a lot of demand. Jonathan, you've probably got the hardest job of all because you've got to take what I want and what these guys deliver and put it all together. So introduce yourself.
Yep. So hi, everyone. My name's Jonathan Pallant. I'm a senior consultant at 42 Technology, based just outside the beautiful city of Cambridge, England. Yeah, I've spent 20 years trying to put together the kinds of products that these great people have put together into a fashion that meets my clients' needs. And you never know what a customer's going to walk in through the door. I've built cameras that have survived winter down in Antarctica. I've built satellite phones. I've built Bluetooth headsets. But I guess the key thing that joins all of these different projects together is trying to get the most out of what you've got and just trying to push the boundaries, push the laws of physics wherever you can.
Excellent. Well, Jonathan, we'll try to put some of that expertise to the test here as we get into some of our questions. One thing that is top of everybody's mind, and it's funny as we're practicing for this session, JLL actually released its sustainability report today. We have made a commitment to be carbon neutral for all of our buildings, and yet I just told you I want to put sensors in every building to better manage them. So let's talk a little bit about the power that's involved with those new technologies. How am I going to be able to use all those sensors but still meet my sustainability goals? And I'll let anybody take that one.
I guess I'll start. One of the things you have to do is manage those sensors smartly. And one of the ways you can do that is to architect your system to have a set of hierarchical power domains that can be managed in a very flexible way so that you can smartly use those sensors and with as little power consumption as possible. That's what we do. We have, especially for our heterogeneous processors, we have a very hierarchical, fine-grained power management strategy, and that helps preserve power. And I think that can scale. That idea can scale.
Yeah, and I think I'd add to that and say it's important to consider the product in the whole, both how it's made, how it's shipped, how it's installed, how long it lives for. You can, I guess there's no point producing a really low power product that sort of sips energy during its lifetime if it was incredibly resource intensive to make and then just gets thrown into landfill when it's finished. So I've seen some interesting new things with recyclable, sort of biodegradable PCBs, which is really interesting in terms of reducing landfill at the end of life. But also, just in making your products live longer, making it so you can repair them and keep them running for longer. That's got to be good from a sort of an energy and resource consumption viewpoint as well.
I'll pick it up from a software perspective. With the amount of silicon that's available, you've got a lot of different things that are low power And if you can do it with a low power device, great. Sometimes you need to balance the needs and put in a higher performance engine. Maybe it's a DSP to do some processing. And so you wake up those components and we'll do some work and then have it power down. We had a customer that was working on a defibrillator, and it had a 5-year shelf life where they could, I think they could sustain 3 different events where they could shock a patient 3 different times, and that could be at the very end of that 5-year life cycle. That was the constraints. And how they did it was looking at most of the time it's asleep. It's just does a wake up periodically. It would phone home once a day to say that status is good. But if an event occurred, then it would wake up the rest of the machine and perform the needed operation.
So I think, in the in development end of this stuff, yeah. So am I here? Good.
Yes.
So I think in development of these, these devices, I think it's important to have, some validation that, things are going the way you expect them to. So I think, in this case of NXP, making sure that the low current states are what you expect them to be, and making sure that over the life of the device, things don't go out of spec. So instrumentation is pretty critical to understanding all that stuff.
Thanks, guys. And Steve, I loved your defib. I definitely want to make sure if it ever needs to be used on me, it's ready to go. So with that as a backdrop, and I don't think people, a lot of people in the world realize how critical these things are and how pervasive they can be. So let's talk a little bit about the factors people should consider when they're managing power consumption. And Rob, maybe I'll start with you. I know when we talked the other day, there were a couple of different areas that people should be looking at and thinking about as they manage power consumption.
Yeah, so we take a kind of a system view when we're looking at power, and the areas that and they all kind of work together. So I think the areas I mentioned were, one is what can you do in software? There's a lot of optimization you can do in software, like Stephen alluded to. There's many techniques available there. But also, it goes beyond just that. It's architecting the device with software in mind so you can take advantage of the right types of APIs and abstractions that are needed from a programmer's perspective. Also, tools. You need tools to be able to measure, like was just mentioned, appropriately, and also documentation. And we're not talking about thousands of pages of documentation, but some sample use cases and practical techniques for how to pull all this stuff together. And then finally, boards. You have to be able to build a board with the device on it that allows you to measure power. And I believe all 5 of them are really needed in a comprehensive strategy for addressing this topic. And so that's the kind of system view that we take.
I love that 1,000 pages of documentation. I'm going to come back to that one in a minute. But for the rest of the panel, what are your thoughts about managing power consumption?
Well, from a system perspective, I mean, certainly we're going to take the parts that NXP produces and read those 1,000-page documents and try and digest all the different states that the machine could be in. And we'll look at the different power islands that are provided and look at ways of optimizing it. Now, when you try and hit the market with all the different vendors and all the different parts out there, there's a big job there in terms of trying to optimize for each one. But you will find some commonality in terms of dynamic voltage and frequency scaling of the CPUs that are there. Maybe we can power down the DSPs or go to some of the lower power cores that are available and do some processing there, and then of course wake up the whole machine when necessary. So that's one method. And the other is if there are power islands that can shut down whole pieces of the chip. It might cause us to reconsider what real time is, and can we tolerate going to the low power states, maybe turning off the device entirely. So we'd have to, when it wakes up, we'd have to go through and reinitialize. Maybe we won't meet timing, so we'll have to keep the device powered, but maybe turn off the clock. And so there's different ways that you can optimize in the system software so that you can achieve the goals of the system.
Yeah, Steve, I completely agree with you. And just to put a use case around that, to reinforce everything you just said, if you look at an application like a wearable, right? Wearables are using heterogeneous devices today, and the use case is very important. Are you doing full application processing where you're computing something for the user? Are you just sensing where you don't need the A core, you just need the M core? Or are you in deep sleep mode where you can turn everything off? So to your exact point, understanding the use case and then applying these different methods, because it is very customer and product centric, the way you approach it.
Let me come back to that 1,000 pages of documentation that Rob mentioned. Probably the last thing you guys want is somebody like me trying to read through and interpret that. And I mentioned the opportunity, especially in my industry, to leverage sensors to drive some value and do it quickly. So how do we do that? What's the right level of documentation for engineers to make it easy, to keep people like me out of it, and to be able to deliver the benefits without having to read through all those pages of documentation?
Well, okay, I guess
this is not an expertise for me, but
go ahead.
Yeah, go. You're the man. So I was just thinking that from the perspective of how we learn things, and you mentioned it before, examples and example code are probably the best things to start with, because that's kind of how we learn. Documentation, especially to that level, to your point, is kind of useless because it's who's going to read through it, right? But examples, I think, are key.
Yeah, exactly. And I think if you can take that 1,000 pages, which is generally right, is the union of everything everybody will want to know, and apply the right filters to that. We actually have tools that pull out certain types of information from the documentation, then we use that to create tooling and things like this. So I think if you're smart about how the documentation, maybe have a programmer's guide, an optimization guide, and then you need the detailed stuff for the guy that's writing the drivers. So it's just, again, instead of putting it all into one document, maybe having different documents for different types of quote unquote customers would help.
So another thing I've seen that's really powerful is when vendors are able to provide parts of their data sheets in a machine readable form. So I think it's useful to try and sort of move beyond the PDF data sheet, because it is an electronic version of a book and it's kind of designed to be read, and then it goes into your head and you have to type it out. I've had a lot of success using what ARM call an SVD file. It's basically a file that the computer can read that describes all of the registers and all of the peripherals in the chip, so that then when I write firmware, and I've got some good tools written in the Rust programming language, which can do this, they can sort of generate that first layer of driver automatically based on this description of the chip. It knows where the peripherals are. It knows I've got 3 serial ports, for example. And that helps me not have to worry about the lower level details and, getting all the addresses correct, because I know the machine's got that. It can, provided the file I'm given is correct and matches the chip, and hopefully the chip manufacturers are doing some work there to make sure that all lines up. But given that, being able to auto-generate that sort of lower layer of the driver just helps me as an engineer concentrate on the more interesting and the more difficult things sort of further up the stack.
Yeah, it's interesting you mentioned that. I've always been a proponent for if you can automatically generate the code. If you think about it, when NXP or another hardware provider provides this manual, they've actually architected it from a system architecture perspective. What is that ideal software interface that's going to drive the peripheral? They know it. But then they translate it through a manual to a software guy who's going to then read this manual and interpret it. What if that algorithm was placed into an intermediate format, an XML file of some sort that could be consumed, and then you'd say standard devices like serial ports or network ports, block devices could all follow the same sort of template. And if we could consume that, then actually generating that low-level device drivers could actually make the job a lot simpler.
So basically you're telling me I don't need to read the manual, and there's help out there for those of us that are interested in sensors to be able to take advantage of some of the new technology. Great. I have a question that came in too. similar line about your thinking on, can you build a low power Linux-based system? And they're not going to let us get away with just saying yes or no. They want to know, if so, how would you do it?
So I'm happy to say this one. I mean, you can build a low power Linux system because, you know, most of us carry one around in our pocket. You know, an Android smartphone is a low power Linux system. I would say to get that kind of battery life, it does sort of require the combined technical expertise of Google and the operating system vendor and the chip vendor. That's probably, you know, it could be an NXP or a Qualcomm or someone like that. And then the designer of the mobile phone. That's tens, if not hundreds of thousands of engineers who have put an awful lot of hours into designing that system. So yes, it can be done. Is it simple? Is it trivial? No, not really. I guess there are some things you can do to make your life a bit easier. My number one rule is if you need a low power Linux system, the lowest power Linux system you can get is the one that's switched off. So, you know, if you can put down a microcontroller, and you can do most of the work with that. You can get that to do the basic analysis and decide, okay, yeah, we're going to need some networking, and we're going to need some of this advanced functionality where it really makes sense to use a big operating system like Linux. Yeah, okay, then we will power it up. Get that running. Hopefully your boot time is sufficiently short that you're not just consuming all your energy budget booting the system up. So get all those services switched off, you know, trim down all the drivers, make sure you've got the bare minimum in there. Get your work done. You know, as we heard earlier, race to sleep. So get your work done as soon as you can, and then switch that thing off and go back to the low power system. I mentioned before I've deployed cameras to Antarctica, and they had to survive the winter, and that's exactly what we did. In that case, the Linux system was a Raspberry Pi. I remember talking to the engineers, and I said, "Does this system have a standby mode?" And he said, "Yeah, you can put this in a low power standby mode." I said, "Great. How do I get it out of the low power standby mode?" And they said, yeah, you'll have to reboot it to get it out of sleep mode." So I said, "Well, I mean, I'll just switch it off then." That's got off is definitely better than standby in terms of power consumption. But yeah, no, that kind of system in that case worked out really well.
Yeah, we have a lot of customers that start on a Linux base, and they'll look to meet some of their system requirements. And you talk about the different types of requirements. Some of them are boot time. How fast can I boot the system? You think about a front panel cluster in an automobile. That's got to be showing the gauges properly within a few seconds. Well, most Linux systems can't boot in a few seconds to the point where they're showing accurate gauges. So we've had to jump through some hoops to optimize our operating system in such a way that we can boot in that amount of time, show some data that's valid, that needed to be there, and then boot some other systems in the background. It's all about tuning the system and bringing it up to the state that you need it to be in.
Exactly. Yeah, we optimize Linux systems a lot too, and we normally our generic Yocto based release is it's a very generic kind of everything on Linux system because we serve mass market. But what we found is that you can definitely get optimizations by just how you configure the system and how you build it, and then of course all the algorithmic tricks like, you know, instead of routing network packets through the kernel, you route them around the kernel, the user space. I mean, there's all kinds of things you can do to optimize a Linux system. But it is, again, just to reiterate, it's very use case dependent is what we found. So there's some overlap, like Stephen alluded to. There's some generic things you can do, but there's also some very specific things you normally have to do in combination to achieve a specific customer goal. So it does take work.
Excellent. Got another question. What parts of the silicon can we turn off and not enable unless we need it to be enabled?
You can definitely turn off access to many of your peripherals, your memory subsystems, your LPDDR. I mean, that's where most of the energy is consumed. It's not in the core, it's in the peripherals, it's in the cache. All these things are normally, it's actually been around for a while. You can turn these things off and on. With software as well. Some of them is automatic. If you're not sensing any traffic over an interface, the hardware will automatically turn off that interface. So some of it's automatic, some of it's software controlled. It's mainly in the peripherals is what we see. But now you have with these multiple power domains, like I mentioned earlier, you can bring this up a level. So it becomes very hierarchical. Peripheral and interfaces, cache, power domains. It's kind of a very hierarchical kind of structure. I think every vendor does it a little bit differently, but it's kind of a hierarchical approach is what we've seen.
I think, yeah, going back to the point you made earlier, the Linux systems tend to be configured with everything switched on, because that gets you to that working demonstration. You can put the example in front of your hires and say, look, yeah, we've got this working, we've got video going, we've got audio. I mean, yeah, I've also got the network interface and the USB switched on, but we don't care about that right now because I'm doing the demo. So then, yeah, go back to that sort of 8,000 page data sheet. I mean, if it's printed, maybe it would be 8,000 pounds. But there's an awful lot of detail in there about, exactly which islands you can switch on and switch off. I've generally found that sort of the basic Linux kernels, sort of the generic Linux kernels, they generally just switch stuff on because that's most useful for people. And then it's a case of sort of going through and saying, okay, don't need the video subsystem. So not only am I not going to load the video subsystem driver, I've got to make sure that the driver underneath that doesn't even enable the clocks and the power into that particular island of silicon. And then I've got to go through and do that for every single subsystem in my chip. And I think that's often an argument for if power consumption is really key for you, then get a chip that's the right sized. Yeah, you can get a very large, very powerful system on chip and switch most of it off, but maybe you'll actually get to the ideal solution sooner if you just start with a slightly smaller system on chip where there's less work for you to have to go through and make sure you're only activating the parts you need, which is it's difficult sometimes because I look at the catalogs of great companies like NXP and you're like, ooh, that's a really interesting processor. It's got extra processors on the side and video and all kinds of shiny things. As an engineer, I love the shiny things, but actually, in terms of building a product, maybe I just want to go back a few pages in the catalog and go to something simpler that has just what I need and not much else.
Yeah, I think it's important to look at the whole product life cycle, and even as you build the system out the first time, you may take some sensors and measurements and quantify what it is, but it's important to continue to measure it. You'll find that every once in a while somebody will update the software and things get slower, and you're like, well, what happened here? Or maybe they've turned on a power island that you didn't expect. And that's where I think you need to look at some of the tools that Mike was talking about and put that into your system. Because if you can quantify all these different power states and you measure it and you put the same test cases down, then you can detect when something goes wrong.
That's a good point. I think understanding the low-level stuff too within the system. A lot of times there's embedded code that people don't even look at or even know is there that could be turning things on. So seeing things like that happen as well. But really good point about updating and that sort of thing. Always good to validate.
Yeah, there's a lot of good instrumentation going on chip these days, almost like a mini logic analyzer getting embedded on the silicon. But I think that visibility is key. And we do a lot of software development pre-tape out, pre-silicon, and even some of the emulation and platforms that we use have ways now of modeling and measuring power because people want that, at first silicon, not a year, 18 months later when we finally figure it out. So it's becoming important enough that tools are coming out even during the pre-silicon, the pre-tape out cycles.
Excellent discussion. A reminder to our attendees to drop your questions in the Q&A tab, as we'll be getting to more of those in just a moment. Steve, you mentioned in our last question, thinking about the whole life cycle, and that reminds me of another cycle, our supply chain cycle, which a lot of us are experiencing shortages in a lot of the component parts that we need. So question comes up, how do you avoid the material shortages, and what happens if your vendor goes out of business that you're using?
Yeah, well, we like to look at it from a platform perspective. You can look at it, maybe you have a low-end product, you have a middle and a high-end, and you can base the system on the same silicon, or maybe different variants of that silicon. A lot of these have system on module providers that have different grades of the silicon. So you could try a low end process. It also gives you the ability, if that part becomes scarce, that you may be able to immediately switch out to another system on module. That's not ideal for your situation, but it doesn't stop the manufacturer. I think that's kind of the second half of this. So you can broaden your reach with different types of products that you're producing, as well as broaden the ability to select different silicon if there's ever a shortage.
I think that the important sort of flip side to that discussion is to remember the trade-offs that necessarily ends up involving. I have seen designs where the use of a good system on module was a good approach because it allowed you that flexibility, it allowed you to switch out. But I think I've also worked on systems where every single square millimeter was critical. Every single spare milliwatt was critical. And so in that particular scenario I'm thinking of, they could have used a system on module, but maybe it would have come with a couple of extra features that weren't strictly speaking necessary. And in that case, it was important to then say, okay, I'm going to weigh all this up in the round. I've considered all my options carefully. And actually, in this case, I'm going to pay the price in terms of a lack of sort of choice in terms of where I can get my parts from. But my payoff then is I get a slightly smaller design that's sort of more tightly coupled to my system requirements, and it takes less power. It's not always an easy question to answer. They're difficult trade-offs to balance.
Let's go to some ripped from the headlines, if you will. There's been headlines about some sensors, for example, in Texas, overheating. So what can we do from a testing perspective to, beat the heat, if you will?
So I thought that the headline of the satellite antennas, we can call them that, overheating in Texas was a really interesting one, because you can and you should, when you design your embedded systems, include automated tests. It's much easier if you can run those tests in a repeatable fashion, so you don't need the engineer to go off and stand in the corner of the lab and run through the sequence written out on paper. It should be every time I do a commit, every time I get a new PCB, we can plug it in the rig and we can run through an automated set of tests. And if you can do that, you can then move your testing maybe to an automated environmental chamber where we can control the temperature, high and low. We can control the humidity. We can, run it overnight for a week, whatever we need to do. The story about these antennas in Texas was interesting because not only were they in a very warm environment, so we had a very high air temperature, they were also getting irradiated by, infrared radiation from the sun was causing an additional heating effect. And then they were also catching reflections off the ground and getting heated from the underside as well. And I don't know what your environmental chambers look like, but I'm pretty sure mine doesn't have sort of a sun simulator inside, and we can't account for the effects of infrared heating. So I guess your only way out of that particular scenario is you have to really consider the environment your product's going to be used in. You're going to have to go through and detail it. Okay, am I outdoors? Am I indoors? Do I have humidity issues? Do I have sort of rain ingress issues? Am I exposed to direct sun? Satellite dish, generally yes, because they don't work well when they're occluded. They need to have a clear view of the sky. It's just a lot of real good old-fashioned systems engineering and analysis required to get you out of that one. There's no real shortcuts that I know of.
Jonathan, us down here in Texas, evidently we're either freezing or we're overheating. We tend to get both within the same month. So anything you can do to help on both sides of that equation.
Will do.
Let's pull another one from the headlines. Then Wall Street Journal had an article about autonomous vehicle and some valuations and some sales. And I know we're all seeing headlines about that. So let's talk a little bit about, autonomous vehicles need higher performance in computing on the edge. So how should people be thinking about taking advantage of IoT compute in the cloud, especially with the safety and the opportunities around that for all of us with the vehicles that will be around us shortly.
Yeah, well, it's an interesting use case because there is the IoT connectivity. 5G is here, so you've got that capability. But yet, when you start looking at autonomous drive, you can't tolerate the latencies. The amount of time that you have to make a decision is measured in milliseconds. If you're not going to hit a ball that jumps out and a boy that's following the ball, and you need to do some collision avoidance, you just can't tolerate going to the cloud. Yet it's important to say, well, what can the cloud be used for? And there's a lot of different use cases that can come about. One is learning any hazards that are in front of you on the same trail or the same map, the same track that you're taking. If somebody's detected a pothole or a bridge out, well, then that would be useful information. It's not time sensitive, but it's definitely mission critical. You're not going to be able to complete your journey. And we do see this in the cell phones. Everybody checks their map before they take their vacation or they're doing their commute to see if one route is better than the other. But en route, to be able to make a dynamic change, which might take it a second, well, that's okay. I couldn't make a life-changing decision in that second, but I certainly could make a decision to take a different route if necessary. So I think balancing the needs of what has to be done on the vehicle and then taking that sensor data and still passing it to the cloud or storing it so that later in the day it can be digested. I know that there's different autonomous vehicle companies that are collecting this sensor data, and they collect it at night. When you're charging, they also pull all this data off the vehicle. And that allows them to do some post-processing, some analytics in the cloud that can maybe look at the fleet of vehicles. You might be able to detect some anomalies going on that are in similar sets of vehicles. Maybe the battery consumption is higher than normal, and you might be able to identify what's going on there. So the use cases are there to take advantage of the cloud, but it's really a question of how do we bridge the gap and decide what needs to be on the vehicle and what can be pushed to the cloud.
Yeah, I think I'd add to that. My experience as a wireless engineer, to be slightly flippant briefly, my experience as a wireless engineer is if you can plug it in with a wire, you probably should. And then my experience as a networking engineer suggests that if you've got anything plugged in with a wire, you should expect someone to unplug it at exactly the wrong moment. And if you work those two into your system design, you think you'll get somewhere.
So you're suggesting that we put more intelligence in the sensors themselves, so that you don't have to worry about the wires or the wireless, right?
I think it's the only solution. It's really hard to rely on wireless connectivity. It's really good for the value add, and for the extra, and like you say, the sort of the sensor data you can fetch overnight. But I can't see a world where you can make mission critical decisions on a sort of a standard commercial wireless network. Maybe if you have multiple networks, maybe you say, okay, I've got 5G and I've got a sort of a backup UHF link and I've got a backup satellite, then okay, the chances of any one of those three functioning at any time gets reasonable. But wireless in general is difficult, and I stand by my recommendation to plug a cable in wherever you can.
You've probably described where about half the help desk problems come from, Jonathan. Somebody unplugging something they shouldn't have at the wrong time. We have about 6 minutes left in this session, so let me ask a question of each of you. I started out by saying that as CIO in one of the largest real estate companies in the world, I predict that we're going to be using sensors a lot more in my industry in the built environment to drive better utilization, create better experiences, better manage our buildings. I think there's going to be a huge uptake in the real estate industry. We're actually making some venture capital investments in prop tech related to sensors. So that's a big change for an industry that's not historically been known for adopting technology early. Let me go around to each of you and get a prediction that you have about the future of innovation for sensors and about power management. for these embedded devices, what would it be and why do you think that? And we'll do that as our closing question. So let me start. Whoever wants to take it first, and we'll just go around the horn.
Okay, I'm happy to jump in first. I think in terms of buildings, the thing that's interesting for me is buildings live a really long time. I say we're based just outside Cambridge. I'll be honest, when I grew up, I thought that's what buildings were like. They were sort of ornate Gothic things built in the 1300s, and everybody has those, right? And then I spent some time in other places in Coventry and going around America, and I'm like, oh, okay, no, this is quite unusual. But as a general rule, buildings live a really long time, and electronics maybe not so much. So I look forward to a world where we can design the fabric of buildings to try and reflect and accommodate what might be coming in the future. All those people who built their houses 20 years ago and they went overboard and ran Cat5 networking cable all around the house and extra main sockets everywhere, and they thought, I don't know if I'm going to need them, but hell, we're doing the plaster work, so let's get all the wiring in now. I'd like to think they're reaping the rewards. And so I look forward to a world where we have buildings that have connectivity and power available, and it's sort of in a pluggable way. So the software engineers and the hardware engineers can keep coming up with new innovative sensing systems and new things to measure and new ways to transmit information, but we can make use of that sort of existing infrastructure without having to tear the building apart every 10 years.
And I'm one that did the Cat5 in the house, but now I've got the wireless fiber that runs faster. So I'll cop to making that investment that isn't quite paying off that way. Let's not limit just the buildings too, even though that was the way I started it out. Anything that you guys are predicting that our audience should be thinking about or thinking differently about based on your perceptions or ideas?
Well, I'll start by looking at the ability to future-proof your design. So in a building, you've got your sensors that are in there now. Maybe there's a better sensor that's coming down the pike, and it's in 5 years. So you're going to want to replace it, or maybe not. It depends on what level it is. Predictive maintenance, to be able to say, oh, that sensor's going out or that feature's going out, and you have enough sense in the building to say, why is this power plant consuming more energy than it used to, or it's something in the HVAC system. So taking care of that to be able to predict maintenance, understand where things are, and then security. I think that's really important when you start looking at some of these hacks that have happened recently. You can go back, 5 years ago, that Target was hacked through their HVAC system. And they were on the corporate network. They were able to see the credit card transactions, and they were stealing data. So that data was costing consumers money, or the banks money, and whatnot. It was an expensive problem that was caused because somebody didn't understand what an air gap was, and they just went, oh, the network's up, we're good. Designing with security in mind from the beginning, so that what we see today and in 5 years, maybe we're going to have to upgrade these technologies. There's going to be new attack surfaces, and today's technology may not last the full time. So how do we deal with the updating of software over that life cycle?
Excellent. Rob?
Yeah, I think the last few decades have been great as far as the economics of sensors. Things have gotten smaller, less expensive. It's opened up just a huge amount of new applications. I think that's going to continue. I think also sensors are going to get smarter, both in processing closer to the sensor, as well as we're doing some things now with machine learning in sensors. I think they're going to get smarter, and I think they're going to get more fused. If you just like us as humans are sensor fused. We have all these sensors in our bodies, and they all work together to accomplish something. I think sensor fusion is going to allow even more efficient processing of applications, and so I think you're going to see a lot more being done in integrating sensors. I think that's called sensor fusion. That's going to be I think a new wave coming.
Mike, you get the last word.
That's amazing, really. Okay, one general thing I will say is that the future is impossible to predict, and what we think is impossible right now will be commonplace in the future because that's always the way it goes. But I do agree with the point of the sensor fusion. I think that's going to be a big part of it. But as the security is probably the number one thing, because we're seeing, a lot of issues with that. And I've been talking to folks in the industry who are working on real-time ways of keeping track of what's going on, and especially on networks. And so I think things like that are going to be super important as well.
Excellent. Well, guys, thank you so much for joining. I can tell you, just in talking to you guys, you give me a lot to think about. You've inspired me. I know we're going to see so many more sensors used in so many ways we're not even thinking about, to your point, Mike. And I think it's why sessions like these are so important for us to keep up and learn from each other. So thanks to the sponsors and to Sensor Week, and to you guys for participating, and to our audience. And with that, I'll turn it back over to our producers.
Thank you for attending today's session of Sensors Innovation Week Summer Edition, and for submitting so many great questions. It's been a great day of education and content. On behalf of Fierce Electronics and Sensors Converge, I would also like to thank all of our speakers for participating, as well as today's sponsor, Nuvation, for their support. I look forward to seeing everyone during the Meet the Speaker Zoom, which you will automatically be redirected to. If you aren't redirected for some reason, please click on the Meet the Speakers embedded track tile on the Sessions tab in the console. Be sure to join us back here tomorrow at 11 a.m. Eastern Time for another day of Sensors Innovation Week Summer Edition. Thanks again, stay safe and take care.